My name is Stefan Mödlhamer. I work for the company TTTech, which is headquartered in Vienna and employs more than 2,000 people and operates worldwide. The company itself is structured into different business units. One of them is the business unit Aerospace, which also incorporates the space department, which I mostly work for. So, TTTech itself is mostly famous for its time-triggered Ethernet implementation, which seems to become the standard for high reliable deterministic Ethernet for safety-critical space systems. So there are a couple of projects ongoing for launch vehicles like the Ariane 6 and other US customers. For human space flights, we have the Lunar Gateway projects and the Artemis missions, and there are also some deep space exploration projects ongoing with commercial partners. So what exactly is time-triggered Ethernet? It more or less is or provides three configurable traffic classes. The first one is the standard Ethernet, as you know it, the 802.3. But also the rate-constrained traffic is handled by time-triggered Ethernet according to RING 664. And for sure, time-triggered traffic according to the SAE AS6802 clock synchronization protocol, which also allows for the time-sensitive traffic communication. So it is in fact, or more or less it provides you with the means to run non-critical traffic together with critical traffic using the same physical infrastructure without both of them intervening with each other. The biggest project so far is the Lunar Gateway program, where time-triggered Ethernet is used by different OEMs and different implementations to be incorporated in different modules throughout the project. And also the GR740 is used here. So for that, TTTech incorporated a small demonstration using one of our main product, the TTE controller space, which incorporates a dedicated time-triggered end system IP as well as two switch IPs running in dual core lockstep mode to ensure for fail-silent behavior in the case if there is an error in the silicon. There's also a Leon 2 FPGA, Leon 2 CPU in the ASIC just for housekeeping and various other modules, so it's more or less a SOC to use. The device comes in two different kinds. There is a plastic housing as well as a ceramic one. The qualification for the plastic was done according to AEC Q100, and the ceramic one is currently ongoing according to QMLV. For the biggest project, the Lunar Gateway, there are at the moment three components available. One is a switch in the 3U form factor, providing 12 Ethernet ports. One of them are gigabit, and the others are 100 megabit. Then there is an end system component, also 3U, which provides 3 gigabit interfaces, and the general avionic hosting unit, which is more or less a CPCI backplane. You can put these cards into and other components as well. So in general, the time-triggered Ethernet network consists out of two different device types, the end systems, which are used to send and receive data. So they're usually connected to a host which wants to communicate with other nodes, and the switches which forward and route the packages sent by the end systems to the other end systems. The way the project was set up with the GR740 was by using the space file link between those two devices. The TT controller also provides a PCI interface and a quad SPI interface to be connected to hosts. But for this project, we chose the space wire with RMAP. In general, when it comes to networking with time-triggered Ethernet, so-called virtual links are used. And in a virtual link, there is always one sender and one or more receivers. And these virtual links have a unique ID and are routed according to either rate constraint traffic policing or time-triggered policing. And in order for time-triggered policing to work, you need to have a synchronized system. So you need to have a global notion of time throughout the cluster. And this is done by the time-triggered Ethernet clock synchronization protocol, which allows for a global notion of time. And this global notion of time more or less provides you by the means to establish a cluster cycle, which is the mark review of the whole system. So after a cluster cycle elapses, the next cluster cycle starts, and the same tasks are repeated in the same order. Within the cluster cycle, we have so-called integration cycles, which are used to, first of all, do the actual clock synchronization and also have some different tasks ongoing. And with this cluster cycle, which is for time-triggered Ethernet used for communication, you can also use this to synchronize your applications running on different nodes, which is more or less what was done in this project. For time-triggered Ethernet, and especially end systems and the hosts, to communicate with each other, the end system provides 3 different ways of sending or encapsulating data using the UDP ports, IP ports, or the MAC ports. So with UDP ports, all the packet and frame handling is done by dedicated hardware within the end system, so the host does not need to bother with that. But it is possible to actually also provide Ethernet packages to the end system. These are the MAC ports if the host application wants to have more fine control how the packages and the frame should look like in the network. In order to use the end system, there are 2 main software components. One is the end system driver, which usually runs on the host, so the GR740, and the end system firmware, which in this case runs on the integrated Leon in the ASIC, which is mostly used for housekeeping and setting up the internal configuration. It is also possible to have the end system driver run on the internal Leon, but if you want to have some performance systems, you are usually better off to using a more potent host computer to do the actual work. So driver-wise, the main functions are, first of all, initialization of the lower hardware. In this case, it's the TTE controller and the end system IP on that. It also is used to provide the initial configuration for the network setup. So all the nodes in the network needs to be configured. For end system, it's rather easy. It's usually provided by the host computer. For switches, there are various means to do so, be it SMP or others. And of course, data transmission and reception are the main parts for the driver. But also status and health monitoring are done in the driver part, so running on the host CPU. For the more interesting part here is how we did the application synchronizations on the different nodes. So usually for RINC 653 compliant operating systems, we use TT-Sync, which ties the major time frame, which is used in these kind of operating systems, to the cluster cycle, and therefore ensure that partitions, so in RINC 653, partitions are more or less the different applications which are partitioned by memory and time to align to each other. And then you can also automatically, because it is tied to the cluster cycle of time-triggered Ethernet, also align the time-triggered communication to these applications. The problem with the GR740 implementation here is that we used VxWorks 6.9, which is not a 653 compliant. So we revert to the means of using interrupts. These interrupts come directly from the end system, and are also triggered by the time-triggered Ethernet clock. So we get an interrupt once a cluster cycle starts or once an integration cycle starts, and we can use this information in the operating system to synchronize the applications running on the node with the other applications running on other nodes. So that's how we achieved the application synchronization here. There were a couple of adaptations needed because we reused some of the software from the Lunar Gateway project, but in Lunar Gateway we used PCI instead of SpaceWire, so we had to rework the lower abstractions there when it comes to communications with the ASIC to include SpaceWire and the RMAP protocol here, and as well route the interrupts we used for application synchronizations from the TT controller to the GR740. Yeah, just to note here it states that we use VxWorks7, but this was the driver for the gateway protocol, but we backported it to 6.9 for this purpose. So this is a picture of the setup. You see at the bottom here the GR740. Then there are two end system cards. These are the 3 units I've showed you before, as well as a SpaceWire analyzer on top of it. With this setup, we achieved a performance of 26 megabit when receiving and 49 megabit when transmitting. In the mixed setup, it was about 35. This can for sure be optimized, especially because the overhead of handling the end system purely over SpaceWire RMAP is a little hefty. So with further improvements on the firmware and driver side, way more bandwidth can be achieved. So we are already approaching the end of the presentation. Here is an overview of the overall setup, which could be created in a block diagram form. So you have the deterministic Ethernet in the middle with the different nodes and the switch, and the different layers which are involved in our usual setup here. So the network interface card, which is usually an end system, time-triggered Ethernet end system, then the host applications with the hosts with different cores, the real-time operating systems using drivers, and usually we also apply some kind of middleware which helps our customers to make work easier with our devices. So, because deterministic Ethernet, especially in the avionics systems, is more or less the key infrastructure between the nodes, because it's the way how you communicate with each other, and having a global notion of time, especially in a fault-tolerant way, clearly helps customers a lot to also synchronize their applications which are executed on these platforms to achieve a more fault-tolerant way of working and executing their applications. Especially with the TT controller I showed you before, having the switch in a common approach drastically improves fault isolation and fault containment when it comes to problems within the silicon or other means you usually would not catch that easy. So as an outlook and final conclusion, application scheduling using time-triggered Ethernet is in fact rather easy to achieve synchronization here, especially for user applications with data communication in between. And also fault tolerant is already baked into this into the time-triggered Ethernet clock synchronization and allows for an easy integration also when it comes to the application space of your projects. So that's pretty much it from my side. If there are any questions, I'm glad to answer them now or in a break or at lunch. Thank you.